Okay, chapter 10. So solving systems of linear equations by graphing, we're going to be able to do this graphically and algebraically. So algebraically we use elimination and substitution. Where systems of linear equations come in useful is in the past, the only equations you could ever solve had one variable. We learned how to solve various types of those equations, but we only ever dealt with one variable. So if we had two unknowns, we had to relate the two unknowns together. This time we can have two different unknown values. So the example given to us has to do with the Smith and Harper family that are attending a charity fundraiser. The entry fee for Mr. Smith is $11, and he has 3 adults and 1 child. Mrs. Harper has fees of $12, which is for 2 adults and 3 children. So we can create these linear equations. We can let x be the entry fee for our adult and y be the entry fee for our children. So for the Smith family, it would be 3x plus y equals 11, and the Harper family would be 2x plus 3y equals 12. So if we were to graph these two equations on the same grid, if we start off with the 3x plus y equals 11, there's various ways that you can graph this without having to use a lot of technology or a lot of time. If your y value has a coefficient of 1, the easiest thing to do is isolate it and make it into that mx plus b form. So now I have a slope and a y-intercept. The y-intercept is 11, and the slope is -3, which means I go down 3 and over 1, and I get a series of points that I can join with a straight line. It is important that you're using a ruler to draw these so that your lines are straight. And if you need a ruler, put up your hand and I will give you one. So for my other equation, I have 2x plus 3y equals 12. And there's 2 ways that I could do this. I could find what my x and y intercepts are. So if I let my x-intercept happens when y equals 0. So if y equals 0, the 3y would disappear, and I would get 2x equals 12. So x would equal 6. And then I have my y-intercept, which is when x equals 0. So the 2x would disappear. So I'd get 3y equals 12, which means y would equal 4. So if I graph those 2 points, x is equal to 6, and y is equal to 0, and then y is equal to 4, and x is equal to 6. I get another line, which I then can join those 2 points with my ruler. So there are my 2 equations. Now something that we need to realize, along this line, every possible coordinate along this line makes that equation true. So if I pick this coordinate right here, which is at 1 and 8, if I plugged it into this equation, it would make the equation true. 3 times 1 is 3, plus 8 is 11. It's a true equation. The same thing happens for all of the points that are on the green line, would make this equation true. So this point right here, what are the coordinates of that point? 3 and 2. And that point appears on both lines. If I plug it 3 times 3 is 9, plus 2 is 11. That's true. Plug it into this equation. 2 times 3 is 6. 3 times 2 is 6. 6 and 6 is 12. So this point made both equations true. It's what we call the solution to the system. It is the point that is the same for both graphs. That's my solution. It's the intersection point. So in the context of this, or sorry, the solution was 3 and 2. And in the context of the question, what did my x variable represent? It's the adult cost. So what is the cost for an adult ticket? $3. And what did y represent? The child cost. So how much does a child's ticket cost? $2. So in a system of linear equations, first of all, the definition of a system of linear equations is it's 2 or more linear equations. So the equations have to be linear, they have to be straight lines, and I have to have at least 2 of them. That's the definition of a system of linear equations. The solution to this system is the point that's common to both graphs, which graphically is their point of intersection. Where the 2 graphs intersect is the point that they have in common. So if we can determine that point of intersection, we have the solution. And that's really what all of this stuff in here explains. So if we look at class example number 1, a system of equations has been represented on the grid. The system has an integral solution. The word integral means what kind of numbers? Integers. So it means that if I look at this point, I can look at the tick marks on the scale, and I'm not thinking that this is some little decimal number. It is going to be how many, what's the coordinates here? 2 and negative 1. It's not 2.1, it's not negative 0.9. Because it says it's an integral solution, I can make the assumption, the correct assumption, that it's going to have to be integers. The solution is that x is equal to 2 and y is negative 1, which as an ordered pair we already have down. So class example number 2 is similar to the first, to the exploration that we did with the Smith and the Harpers, only we don't have the word problem. We have these 2 graphs. So I'm going to give you about 5 minutes. What I want you to do is I want you to graph these 2 graphs and then see if you can determine what the solution is to the system. So let's start working on this. What is the best way, or what method did you use to graph the equation 2x plus y equals 2? The y.
The y-intercept.
So how did you graph it? What did you do?
Integrate 2x to the right.
Okay. So then how does that help me graph it?
I have the y-intercept, which is 2.
Y-intercept is 2.
And the slope is negative 2.
Slope is negative 2. So 2 down and 1 to the right. So then I have a series of points that I can join together to get me my line. Okay. How would you graph this one? Colin, how did you graph this one?
I think I did that one wrong.
How could you graph it then?
Well, I tried to find the m, but
Y equals mx plus
Yeah.
b? Okay, so which one do I want to move?
The y.
The y? So if I'm I move the y to this side, it's going to become positive. And then I need to move the 15 over here. So it would become, and then divide everything by 3. So 15 divided by 3 is, and then I get a 1/3 x. So then my y-intercept is going to be at -5, and my slope is 1/3 positive. So it's up 1 and over 3. So now I have points to join together. And where do these 2 points seem to intersect?
3 and 4.
3 and -4. So the solution would be at 3 and -4.
You said for 3.
Yeah.
Oh, sorry, for 3.
That's okay. Thank you. So if I take a look at the part C says algebraically verify the solution by replacing the values into the original equations. So that means if I put 3 and -4 into this equation, I want to see what I get. So where I see an x, I put a 3. Where I see y, I would have -4. I don't use the equal sign because I'm trying to verify. So I'm using left side, right side. So 2 times 3 is?
6.
And 6 plus -4 is? 2. And then I do the same thing with the other equation. X, which is 3, minus 3 times y, which is -4. So 3, I can remove the brackets. This minus 3 times -4, I'm going to treat the 3 as being a negative as well. So -3 times -4 is, and what's 3 plus 12? So I verified that this solution does work in both equations. Okay? Now the whole purpose behind solving these graphically would be to use your graphing calculator. If you can't use your graphing calculator, you're almost better off solving these algebraically. Because this works because the system was it was an integral intersection. But what happens if they're not actually intersecting on the coordinate grids properly? If it's not an integral solution, trying to graph it, you're not going to be able to get the right solution. So we can use our graphing calculators to solve these systems. To use the graphing calculator, we have gone through part of this. You do know how to graph, put the y equals. So the first thing is your equations have to be in terms of y. So those equations that we were dealing with that were kind of in a general form, we would have to write them into slope y-intercept. They would all have to be a y equals. Once you have the 2 graphs on your grid, you want to make sure that you can see them both, and then you're going to find the intersection point. So this part gives the explanation. We're going to jump into the actual example. So this is the question with the Harpers and the Smiths from the beginning. So if I take my 3x plus y equals 11, and I write it as a y equals equation, when I move the 3x over, it will become negative 3x. So there's my first equation. With my second equation, I move the 2x over, which makes it negative. And then to get the y by itself, I need to divide by 3. So I divide the 2 by 3 and the 12 by 3. So that's what I'm going to put into my graphing calculator. So there's my first equation, and there's my second equation. So I grab my whatever equations you have in for y1 and 2, so y1 equals negative 3x plus 11. And then for y2, I'd use brackets to put in my negative 2/3, which would be negative 2 divided by 3, x plus 4. So we start off with a standard window setting, my zoom 6, and see if I can see the two graphs. So there's my first equation, and there's my second equation. So a suitable window setting could be the standard window setting. As long as I can see this intersection point, I may want to slightly make an adjustment so that I can see this intercept, because I can't really tell where it's intersecting up there. So I could go through, I could get rid of some of my x's because I don't need all of those negative x's. I could get rid of some of my negative y's as well, and then make my positive y's go higher. So if I did that, now I can see the intercepts from both graphs and the intersection point. So a suitable window setting, x's from negative 5 to 10, and y's from negative 5 to 15, I think is what I picked. So now that we have our window settings, we can see everything that we need to see on the graph. It's time to find that intersection point. So it's second calc, and it's choice number 5. So I can scroll down to number 5 and press enter, or I can just simply press 5. And then what comes up is first curve. First curve meaning the first equation, first line that you're on. So I want to toggle over to as close to that intersection point as I can, because I want to tell the graph where, the calculator where to look. I press enter again because it's on the second line, press enter again because it says guess, I don't want it to guess, and then I get intersection. X is 3, Y is 2. And this confirms what we got when we were using the first time. Any questions so far? Okay, so we're going to jump to class example number 4, and then I'm going to go back to the stuff that's written above, because it's easier to look at it afterwards than to try to read it and fit it in before. So this is the following system of equations, and we're going to try to solve it. So instead of x's and y's, we have a's and b's. Doesn't really matter. Pick a variable to isolate. So do we want to isolate b or do we want to isolate a? Think in terms of x and y's. If these were x's and y's, which one would we isolate? If these were x's and y's, I would be isolating my y. So I'd isolate my b. It doesn't matter which one you isolate. What matters is you have to remember what your coordinates are going to be written as. Okay, so if I let my x's be a's and my b's be y's, it'll, when I look at my ordered pair, that's my value for the first one, that would be my value for the second ordered pair. If I went the other way around, I'd have to remember to flip them. So if we isolate for b on the first equation, I would get 7b equals negative 6a plus 5. Divide by 7. And I get these nice, lovely fractions, negative 6/7 a plus 5/7. And then if I do the same thing for 3a equals 14b, I divide by 14, and I get 13a over 14, or 13/14 a, or not 13, 3/14 a. So I could write it like this. So if I put those into my calculator, equals bracket negative 6/7 bracket x. I can't use anything other than x. The calculator will not recognize if I try to put in an a. Plus 5/7. And then for y2, 3/14 times x. Go back to my standard window settings, so that would be zoom 6. There's my first graph, that was the 5/7, 6/7 graph. And there's my second one. So all of my intercepts are quite clustered, quite close. So I could change all of this and I could shrink it up. Instead of going from positive 10 to negative 10, I could go from like a positive 3 to a negative 3. On my x's, the same thing. So if I adjust my window settings, even if I went with 4s, negative 4 to positive 4, negative 4 to positive 4, graph this again, and now I can see a better portion of the graph. Again, to find the intersection points, second calc, number 5, toggle over to be close to that intersection, and then basically you're pressing enter 3 times. And when I do that, what kind of numbers do I get?
Repeat.
I get decimals, I get repeating numbers. So if I wanted to change this, I could do that. So I have these fractions. Anyone know what the fraction would be for 6 repeating, or 0.6 repeating? 2/3. So those ones we kind of know. But what about this one?
100%.
How'd you figure it out?
You just went back to my main menu, alpha 1, and then half.
So if you remember, we talked about this earlier when we were doing the graphing thing. What you do from this point, go back to your main screen. So second quit. If you press your X variable button and press enter, that 0.6 repeating comes up. And then I can use my math frac to change it to 2/3. To get the Y value, like Tyrone said, I press alpha, and the letter Y is choice number 1. And press enter again, and that Y value came up that I just had on my screen. Math frac again, and there's my 1/7. So now I have my solution. So my solution being 2/3 and 1/7. And because we graph them as a B equals, the B value can go second and the A value goes first. So if we algebraically verify this, because this is the fun part, 6 times 2/3 plus 7 times 1/7 is supposed to equal 5. When you are multiplying these fractions, what's 6 times 2/3?
4.
How do you get 4?
Because 6 times 2 is 12 divided by 3 is 4.
Okay, so I can go 6 times 2 is 12. 12 divided by 3 is 4. The other way I can do it, what's 6 divided by 3? And what's 2 times 2? 4. What's 7 divided by 7? What's 1 times 1? What's 4 plus 1? Does that verify it? It does. So now if I look at the other one, 3 times A, and then 14 times B. So again, 3 divided by 3, 1. 1 times 2. So 3 times 2/3 is 2. 14 divided by 7 times 1. And it's verified. So your assignment, questions 3, B, and E, 4, A, and C, 5, 6, and 7. So it's all using the graphing calculator to find the solution to a system of linear equations.